All right. So we did above here, we did this approximation of the area under this curve here. And, we got a rough estimate, right? Remember, again, the actual area is 10 and 2/3, and we're getting some approximate areas. How do we make these approximations better? Right? Well, if you think about it, there's lots of sort of gaps here that we have, either like for the right endpoint stuff here, there's a lot missing here, there's some missing here, but there's too much here and too much here. We can make this estimate a bit better by adding more rectangles. All right? So to get a rough sketch here of what we're saying. All right. So before we were cutting it into 4 pieces, like so. But if we cut this instead into 8 pieces, let's say, so cut these all in half again. Let's draw the rectangles, and let's do left endpoints here. So let's look at L8. Okay. So what I want to write down here is, well, what is L8 going to be? All right, so we're going to have our delta x. Actually, let me move this underneath here. So L8 is going to be our delta x, the width of our rectangles, times f of each of the left endpoints here. All right, so here we have f of -2 plus f of -3/2 plus f of -1 plus f of -1/2 plus f of 0 plus f of 1/2 plus f of 1 plus f of 3/2. Right? So each of those left endpoints are where we draw the rectangles at. I'm going to do my best here. Right? So there's all my left endpoints. And I want to use the left ends to make my rectangle heights. Okay, so here I have 8 rectangles. 1, 2, 3, 4, 5, 6, 7, 8. All right, so let's compute those necessary pieces now. So again here, just a reminder, we're looking at f of x equals 4 minus x squared. Okay, delta x is going to be, again, this is b minus a over n. In this case, b minus a over 8. So we're gonna, well, let's put the n here. All right. So b minus a over n, what does this mean? It means take your end point minus your start point. So this top here is how long this interval is. And then when n says how many pieces to cut it into. This is going to be 2 minus -2 over 8, which in this case works out to be 1/2. All right, so now we just have to, compute all these values. So we have 1/2. F of -2 is 0, plus f of -3/2. We did this earlier. Let's see. -3/2 is 7/4. Right? F of -1 is 3. F of -1/2. Let's see, we did that earlier as well. Is 15 over 4. Right. Let's see, that's those. F of 0 is 4. F of 1/2 is also 15/4. F of 1 is 3. And f of 3 halves is 7/4. Right, so we want to add all this up. Right, so we have 1/2. Let's see. What do we get here? We have 7 plus 3. 7/4 plus 3, so that's going to be 12. I'm going to give all these a common denominator here. The 0 I'm going to leave off. Let's see, plus 15, plus 16, plus 15, plus 12, plus 7. Right? So let's see, that's 19. Let's do this. This is 30. 40, 70. This is going to be 84 over 8. All right? And that's going to be 10.5. All right? So when we do this with 8 rectangles, we get a closer approximation to the true area. Right? This is actually really close to 10 2/3. Right? So you can see here, in order to sort of improve an area estimate, if we kind of shove in more rectangles into the area there, what's going to happen is those gaps that we had get smaller, and those overestimates over here, they also get smaller. Right? So again, compare that to this one, right? When we did 4 rectangles. Again, a pretty huge gap here, a decent gap there, an overestimate here, and a really big overestimate here. Right? Now we go back to 8 rectangles, and we have a much smaller gap going on here, and a much smaller overestimate. Now, the thinner and thinner and thinner that we make these rectangles, the more these gaps sort of get carved out, the more these overestimates get carved away, and we get closer and closer to the actual area. So let's look at this in Mathematica real quick, just to sort of see, what is actually happening here. Right? So here you can see we have the same function here. Let me put this back on left endpoints. Make this picture a little bit bigger. Right? So this is the function we were just graphing and looking at the area of. So here's endpoints when we had 4. Let's bump this up to 8. And again, so okay, good. We got the estimate area correct. And again, look at how much less empty space we have here and less overestimate we have here. Right? And then, if we just keep adding more and more rectangles, you can see that, the overestimates get smaller, the underestimates over here get smaller. So we get closer and closer, this estimated area, to the actual area. Right? And, we can keep doing this. And you can see at some point here, how far did this go? Let's push this all the way to 70. If we push this all the way, this fills in quite nicely. Right? So the more rectangles we use, the better. Right? And the same is true when we go to, say, the right endpoints. Right? In this case, you'll see it's basically the same picture as with the left endpoints, except it's flipped over. And as I said earlier, that's because this is symmetric. Right? And then it actually turns out the midpoint, the midpoint is slightly better because it avoids stuff like completely flat rectangles like this that have no area. Usually, not always, but right. So the midpoint is actually always a little bit better because of the way it fills in space here. So you can see it gets closer to the actual area a lot faster. All right. And, it's kind of interesting to see this work out with a couple different shapes here. So like let's use this one. Or this one. Let's go for this one here. Right? So what we can see here, we use left endpoints, is, again, the more we use, the better the area gets filled in. Look at an absolute value function here, right? And the more we use, the better it fills in. Okay? Now, we'll address this in another video here, but you might have seen something interesting when I popped up something like this. Now, the interesting thing here is some of these rectangles go below the x-axis, right? So think about what that could mean, or what that should mean in terms of, these left, right, and midpoint formula.